reactions. Some chemical reactions are reversible. That means that when you take the reactants and turn them into products, you can then take the products and turn them back into the reactants. We've seen some of before, for example, the ionization of weak acids in solution is an example of a reversible reaction. We represent a reversible reaction using this symbol here. This is the reversible arrow. It goes in place of the normal arrow. That tells us that we can make something and then we can take those things that we've made and we can turn it back into what we started with. Reactants to products, products to reactants. A good example of this would be a hydrated salt. A hydrated salt is a salt that contains water of crystallization, represented like this. So this would be hydrated copper 2 sulfate. This would be a blue color. If I heated that, then the water would escape and I would make anhydrous copper 2 sulfate, which is white, and steam, which is water. I could then take that water and put it back in, and I would make hydrated copper 2 sulfate again, which is blue again. So that shows that the reaction is reversible. If you do a reversible reaction in a closed system, so nothing gets in and nothing gets out, you can set up what's called an equilibrium. And that means that you'll have some of your mixture will be as the products and some will be as the reactants, and they're changing into each other all the time. Okay? But once you've reached equilibrium, what that means is every time you have something changing that way, you have something changing that way as well. So overall, the concentrations don't change. And the speed or rate at which they change into each other is the same. It's 1 for 1. So your definition for the exam of equilibria is very specific. Make sure you just memorize this. It is that the rate of the forwards and the backwards reaction is equal, and the overall concentrations of your reactants and your products do not change. The rate of the forward and backwards reaction are equal. The overall concentrations do not change. Don't mix those up. If we have a closed system and we set up equilibrium, what we can do is we can change the position of equilibrium. Now, what does that mean? It means that we can move the concentration over more to one side or to the other. So for example, if I set up an equilibrium and I have more of my reactants than my products, I can change the conditions and I can make more of my products and less of my reactants, and a new equilibrium will set up. So I can change what's called the position of equilibrium. And the way we describe that is by saying it moves to the left or it moves to the right. If it moves to the left, it does more of the backwards reaction and we get more of the reactants. If it moves to the right, it does some of the forward reaction and we get more of the products. So how do we change the position of equilibrium? Well, there's an idea called Le Chatelier's principle. Le Chatelier's principle, in simple language, states whatever you do to a closed system at equilibrium, it does the opposite. So if you increase the temperature, it will decrease it. If you decrease the temperature, it will increase it. If you increase the pressure, it will decrease it, and so on. So let's have a look at how that affects the position of equilibrium. So let's say I have this made up equilibria here, not using real chemicals there. And whenever you have a reversible reaction, one of the directions will be exothermic. Exothermic means it releases heat. And one of the directions will be endothermic. It means it takes heat in. So I will pretend for this one that my forwards reaction is exothermic. So if I increase the temperature, I have made the temperature higher, it wants to make the temperature lower. How does it do that? It does more of the backwards reaction, the endothermic one. So increasing the temperature will cause the endothermic reaction to happen more. So in this case, it will shift the equilibrium to the left. Not always the left, make sure you know which one's the endothermic and exothermic reaction. But increasing the temperature moves the position of equilibrium towards the endothermic side. And if I decrease the temperature, if I make the temperature go down, it does the opposite. it tries to increase the temperature by doing the exothermic reaction. So by decreasing the temperature, I can move my position of equilibrium more towards the endothermic side, the exothermic side, it does the opposite, and I can make more of the products. What about pressure? Well, if you've got more particles, that's a higher pressure. So high pressure is going to favor the side with fewer molecules. Remember, pressure only applies in gases, so the full definition there is high pressure favors the side with the fewer molecules of gas. So we can see that on the left we've got one molecule. On the right we've got two molecules. So if I increase the pressure, it's going to favor the side with fewer molecules of gas, it goes to the left. If I decrease the pressure, it moves to the side with more molecules of gas, it goes to the right. Again, rewatch that if you're not sure about what I just said. The other way that you can shift the position of equilibrium actually involves breaking the closed system. You can change the concentration. If you take out some of the product, you've lowered the concentration. Le Chatelier's is going to try and increase that concentration again by making more on that side. If I put more in, it's going to change to the other side. So it's going to try and decrease that concentration. So to summarize, Le Chatelier's principle states, whatever you do to a system at equilibrium, a closed system at equilibrium, it does the opposite. That means increasing the temperature favors the endothermic side. Decreasing the temperature moves the position of equilibrium to the exothermic side. Increasing the pressure moves the position of equilibrium to the side with fewer molecules. Decreasing the pressure moves the position of equilibrium to the side with more molecules. Next time, we'll have a look at some specific reactions that you have to know, which involve the use of equilibrium, but this was just the equilibrium summary. All right, thanks for watching.